My formal rule. Okay, welcome everyone. Good morning and good afternoon, good evening from all over. It's a pleasure to have this seminar by Tomer Az. This is his formal master seminar talk that we're doing at Acneon. Uh, just a few words about Tomer, and I'll give him the stage. So Tomer actually did his undergraduate at a very early age during high school, originally in physics, then made this really impressive shift to both aspects of mathematics, data science, and AI during his master with us. And now, what you'll see is that he took a pretty ambitious project that also for us, and I think for many around the world, is a unique, in many ways unprecedented, in attempting to connect modern AI tools, especially what LLMs can give us, with computer algebra systems, especially with symbolic methods for computation. This is something that has been attempted in a few places so far, and the right way to combine such tools, the established methods for symbolic computation with modern AI tools, is something that is still being investigated in many places. And I think what's one of the beautiful things that we have here in Tomer's work is actually very successful results and seeing how we can unify mathematics through this approach. So he will talk about the achievements we already had and some of the work that is still being done in the group, and part where we are now headed. And we're happy to also have everyone join in and ask questions. Feel free to ask questions along the way. If we see that they are taking very long, I may ask you to keep some of the questions to the very end. And there we'll open the floor for questions. And with this, I think, Tomer, I'll give you the stage. Looking forward to your talk.
Okay, so thank you so much for the introduction, Ido, and thank you so much everyone for joining today. It's really an honor. I can see all these people around, and really thank you so much for joining. Today's talk will focus, as Ido said, on a new approach to mathematics and even science that we believe will get increasingly important as time advances. And what I'm talking about is integrating AI with external tools. This is a vision of a growing community, and here we'll show one of the first examples of integrating a computer algebra system and LLMs to address a problem in number theory on a large scale. So I'm really excited to share our results, and let's get started. So science needs automation. We see that the number of publications coming out on a monthly basis is skyrocketing. It's growing exponentially. And an automated system to address this that would automatically harvest and validate useful information, make connections, and then move on to discovery, that would be very useful in all of science. Of course, we need to do a few things to make this happen. We need a common language to talk about all of these previous discoveries made, and we need algorithms and formalism to make connections and discoveries. So this is the goal of the system we have in mind and the system that we've built. And it uses LLMs and symbolic tools to achieve this. Of course, we also need a field on which to demonstrate. And there are examples in science for bootstrapping previous work on a large scale with AI. Some of the most important examples, the most impactful, are AlphaFold. For instance, is AlphaFold, which utilized hundreds of thousands of previously known 3D structures of proteins to advance and build a tool that can now predict with high accuracy the way that many uncharted proteins fold, which is useful to biologists, chemists, and many, many different fields. Another example for taking previous work and using that to build new tools is image generation, diffusion models, DALL-E, for example, using many images previously created to now be able to, on demand, create new images. So what if we could have an AlphaFold or a DALL-E for math? One of the things that we are working on with this project is building a building block to do this in math. And that building block is unifying math theory. Of course, AI for math is a big buzz these days. There are many milestones recently made, including achieving a silver medal last year in the Math Olympiad by Google DeepMind. This year, they actually achieved a gold medal using advanced reasoning, combining both. Last year, it was alpha proof and alpha geometry 2, and this year, they used a new version of Gemini. Alpha Evolve, which is a new approach to use evolutionary algorithms, was able to improve the kissing number for 11 dimensions. The kissing number problem is how tightly can we pack spheres in n dimensions. And they actually increased that using an iterative AI approach, which is amazing. Other directions for implementing and doing AI for math is formalizing math in formal systems like Lean. Kevin Buzzard, for example, from Imperial College London, is working on formalizing all of Fermat's last theorem, at least all results from, I think, the late 80s in Lean. And this will expand the database for rigorously and formalized theorems that can then be used to train new AI models. And lastly, I'll talk about FunSearch really quickly. FunSearch was able to improve results in combinatorics and find heuristic algorithms for bin packing, also using this external evaluation for an LLM approach. So if there's something in common here that we see as a trend, is that LLMs can be integrated with external systems that both evaluate and verify the things that the LLM creates. So this is where the community is gravitating towards. And of course, there's a huge competition also between different LLMs. Math is used to gauge LLM reasoning ability, and this is spawning tons of benchmarks and creative evaluation techniques for LLMs. We need hard problems on the one hand, but we also need a way to mitigate trained data set contamination with test data. And a recent work by our colleagues, Michael and Rotem from our group, built a creative way to benchmark LLMs by introducing symbolic perturbations to known problems. So an LLM could have been trained on, for example, the integral we see on the left, but the perturbed version that we see on the right means that the LLM needs to understand in some way the core methods of integration to solve this problem. It can't just memorize the integral on the left to solve the integral on the right. So this is one direction also where things are going, the huge competition between LLMs. Our group, specifically the Ramanujan machine, is working on AI for number theory. This is where we specialize, and we're developing algorithms to discover new math. What we see on the right is the first project done by the group, which started as a search algorithm for formulas for mathematical constants. This led to specialized numerical and symbolic tools and discoveries, a few of which are shown here. So a few recent milestones from the last year include, on the top right, discovery of a generative mechanism for mathematical constant formulas. We'll talk about this more later. And on the left, we see the first unsupervised ML, machine learning for formula discovery, which was published in NeurIPS last year. Also, in ICLR last year, iClear, Itai from our group published a new method of generalizing formulas and finding connections between mathematical constants. And this led to generalizations of Ramanujan's famous formulas for pi times e, which is very, very cool. The full list of publications is on the website, of course, and I invite you to take a look and explore. So we specialize in number theory and in mathematical constants, formulas for them, for example. And the reason why we do this, or why we are interested in them so much, is really that they are everywhere, from the spirals of a flower to the mass distribution of a galaxy. in architecture, in art, and of course, pure math. And of special interest are irrational constants because they require rational approximations to be useful. Um, One of the most famous constants we all know, of course, is pi. The Egyptians had an approximation for pi that allowed them to compute areas for plots of land, which was important for taxation and the economy. And over 1,000 years later, Archimedes found the first rigorous method of approximating the value of pi by circumscribing and inscribing polygons in circles. So over the years, many different ways to compute the constant, to compute sequences that converge to the constant pi and other constants have been found, some of which are here on the screen, like Gauss's formula from 1813, which was an especially efficient way to compute the constant. Ramanujan beat Gauss in terms of efficiency 100 years later and found the formula on the bottom right. And this formula, or part of the formulas that Ramanujan found in a paper in 1914, he published 17 conjectures. Not all of them were proven until the late 1980s, which is incredible. It also paved the path for a new branch of math called modular functions. By the end of the last century, we have Bleyy, Borwein, and Plouffe's formula, which for the first time allowed computation of direct digits of pi, in this case in hex. And so if there's something in common between all these formulas, is that each of them required an impressive or genius mathematical intuition to create these formulas. But there is no systematic method of finding connections between formulas as of yet. There is a lack of a centralized theory that generates the formulas. And why would this be of interest? Well, finding the underlying connections between formulas could be able to shed light on new hidden math and maybe open the door to on-demand formula generation, which is a subject of interest in the AI for math community. We call this problem of finding the common ground a unifying theory for these formulas, the unification problem. And the solution we propose here has three parts. The system combines LLMs and symbolic algorithms. It's a rare union at the moment, but we believe it will become increasingly important in the future in AI. So the system contains three parts: harvesting with validation of these formulas, and then we have clustering and unification. The clustering and unification rely on a combination of numerical and symbolic tools, including a new symbolic algorithm. And the unification relies on a newly discovered mathematical object, which we'll get to in later. Unification, of course, is important in science. Maybe the most far-reaching example, at the risk of sounding a bit presumptuous, is Maxwell's theory of electromagnetism, which unified various phenomena in physics. And this introduced a method of developing theory and observing different phenomena from one lens, which of course led to the modern, many different important technologies of the modern world, including there's a satellite here. This, of course, also helped develop special relativity after noticing some paradoxes. And this required a new theory, which led to special relativity. Category theory, which is symbolized on the bottom right by a commutation diagram, also is a form of unification in math. So unification is important in all of science, and who knows what different new discoveries will be able to be made under a new lens. So are there any questions about the general approach before we dive into the first part? All right, okay, so let's dive into the first stage, which is harvesting equations. To begin the harvesting scheme, we access arXiv, which is an open source database of a few million articles. It's constantly growing, and we access about 500,000 articles in mathematics. This leads to 300 billion different equations, all in LaTeX, and out of those, 120,000 contain the symbol pi. On the right, we can see an example, which is going to be a positive example, but of course, many and most of the equations gathered are not positive examples of pi computing equations. What we're trying to do is find equations that compute the constant pi and generate rational approximations so that we can find a unifying theory for these. And at the moment, we have 120,000 that contain the symbol pi. But we need a way to identify which actually compute pi. And to do this, we use LLMs. GPT-4o Mini decides whether an equation can compute the constant pi, and then a better LLM begins to classify more finely into type of formula, after which it's translated into code, which we can later use algorithmically. So this leads to about 700 formulas, which can be reconstructed and computed in Python. The product is formulas after this stage. Of course, we don't yet know whether these formulas actually compute pi. The LLM only thinks they compute pi, and that means we need a method to validate. And so we use a numerical algorithm, which both validates that the formulas are actually pi formulas, and it also reconstructs the limit of the formula automatically for us, which is great because it takes the burden of some algebra off of the LLM. This is where LLMs tend to fail sometimes. So the result is over 400 formulas, different symbolic structures that all compute the constant pi. And there are a lot of them, of course. What we're missing before we move on to the next stage of the pipeline, maybe I'll ask if there are any questions about the harvesting first. All right, okay. So the next stage, once we have all these formulas that have been validated as pi computing, we can begin to cluster them. And the first stage of clustering is transforming various symbolic forms, symbolic structures. We have both series and continued fractions into a common language, so we can talk about both in one way. So one way to do this is converting them to recurrences. Recurrences can unite different infinite processes into one mechanism. And so, for example, these continued fractions are converted into a sequence of matrices. And of course, a continued fraction leads to a sequence of rational approximations, in this case, for the constant. The same is true for the matrices, right? We can multiply by another matrix to obtain a new approximation for the constant. So it's an equivalent way to get to the same sequence, which converges to the constant of interest. I didn't mention, but of course, pi is only an example for how we can do this. And the method that we talk about here is relevant for many other constants. And in general, for science, this is what we hope to convey here. Recurrences, of course, are great for many different symbolic structures. And given the recurrence and the proper initial conditions, they can reconstruct the original formula. At the top, we have product, in the center, continued fraction, and below we have a series that computes pi. Conversion to recurrences as representations already unifies formulas that look different at first sight. This is what we see at the bottom of this slide. We see two formulas that at first sight, I'm sure there are people in the audience here who would see that these are actually the same formula. But at first sight, they look different, and recurrences automatically translate them into the same canonical form. So canonicalization forms and serves as the first connecting mechanism. We do this with an algorithm by risk. we have our friends from RISC connected here. Thank you for joining. And we use their algorithm called guess to convert different sequences of rationals into polynomial recurrences. This is what we can see on the screen here, represented schematically. So the result of this stage is a collection of matrices that embody the original formulas, and we can move between them at will, actually. And this common language prepares us for making deeper connections algorithmically. How do we make these connections? This is the novelty we introduce in terms of symbolic algorithms. We call the algorithm UMaps. And what it does, given two recurrences, A and B, is build a ladder between them. This ladder is called the co-boundary condition, and it's represented by this equation. It means that we can travel first along AM and then up U at n plus 1, and this will bring us to the same place as traveling first up UN and then to the right by BN. So it shows they're equivalent and they can be computed via each other, these two recurrences. The equations needed here are nonlinear. They're NP hard, and this makes this algorithm hard to, it's a challenge. We don't know, we needed to devise a method to circumvent this nonlinearity. One option was SMT solvers, which are generally heuristic, meaning they don't always work. And that means basically that we needed a trick to solve these equations. Before we get into that, there is one more element to how this algorithm connects different formulas, different recurrences. And that way is first by equating their convergence rates. If we have one recurrence that converges twice as quickly as another recurrence, we would want to first make, for example, 2 steps of the slower converging recurrence equal or comparable to the faster recurrence. This is what we see here. We call this process folding, of taking a few steps of one recurrence and trying to match them against one step of the other recurrence. And that leads us to this equation here. The F represents the folding. So we still have a question, an open question here that we're about to address, but that question is, how do we circumvent the nonlinearity of solving the co-boundary condition? The nonlinearity is a result of solving over the rational functions. That's what we can see here. We have 3 different unknowns, 2 polynomials, PA and PB, and we have the unknown co-boundary matrix, U. And because these are multiplied, we have quadratic terms, and that's the nonlinearity that we have to find how to circumvent. And so the key observation here was noticing that we can relate the limits of the 2 recurrences by the first rung of the ladder, by U1. And this is the lemma that's shown here. U1 relates the projective limits of the recurrences. And through this lemma, we can extract the first rung of the ladder. After this, we can find as many rungs of the ladder as we like. We can find measurements of the co-boundary matrix. And that's what we can see here at the end of this process. Using the co-boundary condition, we propagate and find as many measurements of U as we like. At this point, we have measurements of the co-boundary matrix, but what we'd like is a functional form for it. We want U11 as a rational function, for example, and the same for all the other elements of the matrix. And so what we can do at this point is apply a fit to these empirically gathered values. And once we do that, we have a hypothesis for a co-boundary matrix, which can then be substituted back into the co-boundary condition to verify that indeed we have reconstructed the co-boundary matrix. And that is what we do. And we test the hypotheses and find true co-boundary matrices. And this allows us to connect formulas 94% of the time, meaning 94% of the 400 over 400 formulas that we connected can be connected in this way to at least another formula out of those 400. And these include famous examples like Gauss's 1813 formula and a formula by the Ramanujan machine, the original paper of our group, which was published in Nature. And this formula is one of the first discovered algorithmically by a computer in 2021. And so these formulas are now connected by the coboundary algorithm UMaps. Another example is formulas by Ramanujan and a more contemporary formula. These two were also connected using UMaps. And it's interesting to see that formulas from different centuries that were discovered hundreds of years apart can now be unified into one framework, meaning they were connected using both the harvesting and algorithms after that. So this concludes the second stage of our AI symbolic demonstration, and we found connections between formulas collected and validated. Are there any questions regarding the second stage?
Yes, could you go back just very shortly? You mentioned how you map the different formulae to recurrences. So we
Yes.
saw how that's done with continued fractions, but could you touch on other, not all formulas are given as continued fractions, right? So do you have a similar process for a sum, a product, etc.?
Right. Okay. Thank you so much for the question. This is a good question, and it's addressed by the algorithm by RISC. RISC, the Research Institute for Symbolic Computation, which we have many friends from here connected to the Zoom today, developed an algorithm that can take rational sequences and find the recurrence behind them. And so this is a method that works beyond continued fractions, beyond series. It works for any rational sequence that can, in principle, be converted into a polynomial linear recurrence. So that's how it's addressed. And it also works for recurrences of high order. The examples I showed here, I believe, were mainly up to second order, but of course, this works for high order recurrences. Does that answer the question?
Yeah, perfect. Thank you.
Thank you so much. Okay.
Yeah, maybe another question. So you can guess the recurrence, and of course there's no proof that the recurrence is correct. So you continue from that recurrence under the assumption that the recurrence is correct, right?
So
Or do you verify the correctness of the recurrence also?
Yes, thank you again for the great question. We do verify the recurrence. We substitute the original formula back into the recurrence, and then we obtain a giant expression, which we would want to equal 0, for example. But it's also hard sometimes to make sure that these expressions are identically 0. And so we devised a numerical approach to this problem, and we substitute many, many random numbers into this giant expression, which is supposed to equal 0. And our requirements for being close to 0 are stringent. We need at least 30 substitutions, meaning all 30 substitutions, to lead to a numerical value of under 10 to the minus 10. And after that, we are settled and consider the recurrences true and okay.
Would be interesting to see these expressions if one cannot verify correctness on the symbolic level without numerical evaluations, because then it's really a rigorous proof.
Yes, that is a good point. It's a subject that we have yet to look into, rigorously showing this point. Thank you for
Tomer, go back for a moment. You got muted by mistake.
Whoops, sorry. Thank you for catching that.
Very good.
Okay, so the third and final stage of our approach is unification, meaning finding a centralized theory behind the formulas. As part of the vision for this approach, we use a newly discovered object that generates formulas for mathematical constants. A recent 2024 paper by our group, by Rotem, discovered this object by mining big data on formulas, and it was found to hold many existing ones, which we'll show later. The structure is an infinite lattice where each direction corresponds to a formula, and walking in this lattice corresponds to matrix multiplication based on the point in the lattice. So two things to keep in mind here. Each direction in the object corresponds to a formula, and walking along a line means matrix multiplication. So we can see this action visually via this beautiful video created by Michael and Eyal of our group. We see that starting from the origin, we can walk in different directions. And walking to the right requires multiplication by a right walking matrix. Walking up requires a matrix that corresponds to the up direction. And the interesting property that defines this lattice is that there's a path independence, meaning if we walk between any 2 points in this lattice, what we'll see in just a minute is that we arrive at the same final matrix. And this allows us to associate each point in this lattice with a matrix, which generates an approximation for the constant. So walking in different lines and hitting points along this line can allow us to generate a sequence that converges to the constant of interest. This is what this beautiful video shows. The path independence property gives this object its name. It's called a conservative matrix field, an analogy to a conservative vector field from physics. On the bottom, we can see the three matrices of the pi CMF. The pi CMF is three-dimensional at the moment, and we hope to enlarge it and find additional CMFs that are both of higher rank, meaning 3x3 matrices or even more, and of higher dimension, meaning more directions that we can walk in, greater than 3. One of the great milestones of the CMF was recreating Apéry's 1979 proof of zeta 3's irrationality. And it's amazing that this result came out of a direct big data approach. So what did Apéry do in 1979? He found a very good formula to compute zeta 3, a formula that converges in the right way so as to prove that the constant is irrational. And what the approach with the CMF allowed was both collecting and unifying different formulas for zeta 3 that were found in the mining process. But it also allowed, while most simple directions in the CMF did not recreate Apéry's result, it allowed walking in new directions. And walking along the diagonal, in this case, generated exactly the formula by Apéry, which shows how a big data approach and unifying those results recreated a non-trivial result by Apéry, which was found by some genius intuition. So we've turned Apéry's genius, it remains, of course, as that status, in that status. We found an equivalent approach that takes it and uses big data. So how does this connect to our unification of formulas? Well, parallel trajectories in the CMF, parallel lines, are a coboundary. And this means that we can find our formulas embedded in the CMF by taking a smaller amount of representatives. So each direction corresponds to a recurrence of the CMF, and each recurrence taken from the CMF can be fitted and tried to be connected to the recurrences that we found for the formulas via UMaps. So all in all, we use the same symbolic algorithm to find the 400 formulas, or try to find the 400 formulas in the CMF. And the result, as of now, is that 46% of the formulas collected for pi are unified by a single CMF. And we believe that we can complete this journey and reach 100% if we continue to develop the CMF and the algorithms that have allowed us to unify this amount. So a few examples here, we can see formulas by Gauss, by the Ramanujan machine, by Euler, and other contemporary mathematicians. And all of these are now unified and generated by one structure, one symbolic structure. And of course, there is yet work to be done. 46 is not 100, and so the game is on. The method works for any constant. We've applied it to zeta 3, to Catalan's constant, to E, and other constants. These are some examples of formulas that were both connected to each other via UMaps, and then also unified in an appropriate conservative matrix field for those constants. So all in all, the approach is promising. And taking a step back, a bit of a zoom out, the relevance of the whole system together and to NLP of symbolic math is perhaps something we can apply forward to other branches of math and science. We can imagine, for example, instead of a data set of pi formulas that we'd want to try to get, we could imagine formulas from from particle physics that we'd want to find a theory behind and unify. So this is what LLMs are great at. They're very general. And when we combine them with rigorous validation tools, we can both create understanding and collect that useful data very efficiently. So this was one of the first successful symbolic tool integrations, LLM symbolic tool integrations for math, and one of the first targeting math and number theory. Perhaps number theory is better. So where is this idea of combining LLMs and tools going next? Well, there is a lot of buzz around LLMs for calculus and other core tools in science. We talked about Asimov by Michael and Rotem from our group. They used symbolic perturbations to assess how LLMs actually know how to apply tools from calculus and other branches as well. And there are many new benchmarks that try to gauge how LLMs are doing in integration, for example. So a project we're now working on aims to build the strongest integral solver. And as part of that challenge, our friends at Risk are helping us create challenging integrals. So Yiman, who I believe you are connected to the Zoom, helped us procure the first benchmark that we use to test both computer algebra systems and LLMs separately. And so already this showed that combining the two together, LLMs and symbolic tools, is better than each of them separately. You can see in the rectangle that is highlighted here that SymPy solved 2 out of the 6, and Gemini without SymPy solved an additional 3. And then when we combined the two systems, they solved 5. So as you can see, there's also one integral here that was not solved by any system. And that's the integral we can see here on the screen at the moment. Thank you, Yaron, for this example, as well as the others. And so I asked the LLM, in this case GPT-4, please solve this indefinite integral. And it says, I'm sorry, this integral does not have a known elementary antiderivative. And so being a pesky master's student, I try to make it understand that maybe there is a solution. I tell it there is an elementary antiderivative, and it says, okay, you're right. Thank you for the correction. I'll go solve it for you now. What happens after this? Well, the LLM thinks a lot, and it replies and returns this answer. which is wrong. The correct answer is this answer. So LLMs are not strong enough on their own. It even tried to convince me by computing the integral in SymPy, but SymPy doesn't know how to solve this integral. So the LLM in this case kind of hallucinated its own explanation for why it was correct, and so it did not solve the integral properly. To address this problem, we are building the system called Integrate that aims to be the best integral solver. This is an ambitious goal, and it relies on combining LLMs with a variety of tools, and very importantly, also a validator. So the interplay between LLM, tool, and validator can help us find solutions to integrals that none of these systems separately would have found. And the system we believe will work is a modular system, so we can swap out LLMs and add in tools, and maybe in the future also introduce scheduling and RL. So this is a lofty goal. Stav is currently leading this effort, and we're looking forward to integrating with more integration tools, including novel methods being developed by RISC. So an example here for an integral that the combined system solved, but not Wolfram or GPT independently, is the following integral from one of the latest benchmarks for integration. And what we see is that the LLM did a bit of wandering around in the darkness. It first tried a substitution, but then it used what we call the sum machine to convert the original integral into an infinite sum, which was then validated. And so once it was validated as being equivalent, the LLM said, okay, let's try giving this integral, which is now also an infinite sum, let's try giving it to a computer algebra system. And once that was done, Wolfram language successfully solved that series, and it was validated. And so the LLM got a closed form solution and a stamp of validation, and it returned the correct result. This exemplifies how this approach could be strong, and we hope to continue to develop it in the near future. This is both a modular and versatile project, and it can be extended, hopefully, to many other aspects of science. The vision is that bridging the missing gap in LLMs for verification and robustness, and leveraging really the huge wealth of tools that have been developed by humans over the years, we believe that union will lead to stronger systems on both fronts. So to summarize, discoveries are constantly being made. Big data on these discoveries could unlock future breakthroughs, and LLM symbolic partnerships are powerful enablers of this vision. And that is what we hope to continue to do here at the Ramanujan machine. Thank you so much for listening, and I would love to take questions if there are any. Maybe before that, just one more note. I remembered, Karsten, you asked a question of whether these recurrences were validated. And in fact, I think we use now a new tool, a Maple tool. I forgot its name, but I will check, that uses an algebraic method beyond my understanding, of course, but it uses a method that that does make sure these recurrences are both minimal and true. So yes. Any
Thank you, Thomas.
questions?
This is a really great job, a great talk. It was very well done. We're opening the stage for questions, and happy to connect with people for a longer discussion as well. If anyone is interested in following up later, so let's first see if we have questions from the audience. Yes, Bruno. Oh wait, we see that.
I think, are you muted, Bruno?
Yeah, now we can
Okay,
hear you.
sorry. Yes, you showed one integral on the maybe last but one slide, and you said this was not known how to solve. Could you show this slide again? Yeah, yes, this one.
Yes.
Now, it seems to me that this is the integral is an elementary transcendental function, and I'm not a specialist in this area, but surely Carsten immediately would notice by Risch algorithm, this should be solvable, or at least it should be possible to decide whether it has an integral, which again is an elementary transcendental function, right?
Yes.
I would pass to Yaman because she implemented this and generalized the Risch algorithm. So if somebody knows if it works, then Yaman. Yaman, what do you say?
Integration because it involves algebraic functions. For me, for our my PhD, how I didn't do anything about algebraic functions, but maybe we can choose risk maybe for the free class because the class Mary Bernstein implemented some integrals maybe involving algebraic functions in the free class.
So
Just yeah, it is maybe you can check it. We can construct
okay,
a differential field that it
yeah, yes. So if
Liouville extension. Yeah.
if I understand correctly what you're saying, it is the square root function in this integral which makes it more difficult, because then the original Risch algorithm is not applicable, right? Is this what you say?
Sorry, my internet is a weak.
So I would like to clarify one thing, if it's okay. What I meant to say in this slide is that Wolfram Alpha, as a computer algebra system, did not manage to solve it on its own.
Okay,
And
okay.
independently, GPT also could not solve it on its own.
Yeah.
But the unity,
So this, yeah.
I think you're right about the Risch
Yeah,
algorithm
this
because
is
it is
so
elementary.
two different questions. No? One question would be whether one of the very general, provenly correct algorithms, like, for example, Risch algorithm or any extension to this algorithm later, would have in its range of applicability this particular integral, which I thought is the answer is yes. And another question is whether a system like Wolfram or Maple or any other system has a full implementation of this algorithm. And so I'm not knowledgeable about it. I'm just asking. And of course, this is some way, it's astonishing that these very powerful systems would not have a complete implementation of such a fundamental algorithm like Risch algorithm, for example.
Yeah, it's actually it's a good point. The Risch algorithm, which is today
Yes,
the most powerful method for
yes,
the indefinite integrals, is
yes.
currently not implemented fully in the most
Yeah,
advanced simple Mathematica.
exactly. This,
Yeah,
of course,
yeah,
this is in some way deplorable, because it is known how this algorithm works, and of course it should be implemented before one tries, say,
yeah. But
methods which are not
we do have
really
examples.
algorithmic, but which try to guess and then validate, which of course is a great idea, but I would be a little bit disappointed if the general methods that are provenly correct still are not implemented in the modern systems, which is interesting, very interesting. Yeah.
One of our goals
Yeah.
is I'll go back one more slide. One of our goals is adding in the FreeCast system to the tool collection. And once we do that, we'll have a full Risch algorithm implementation available for the LLM to call. The downside is that both the LLM might not fully understand how to utilize this, and also Rish could be less efficient sometimes. This is a possibility.
This is a very good point because I just came back from Japan, and of course they are doing completely different things, but in the same spirit. Namely, just as an example, to take a grammar basis algorithm, which we know that it works and it works correctly, it's provenly correct, but by using LLMs, for namely neural networks for the computation of grammar basis, it works only maybe in 96% of the cases, which is not good enough for algebra. But anyway, afterwards it can be validated. And the real point is that hopefully these algorithms, at least for some classes of examples, are much faster. And this is the point. No?
Yeah.
So we sacrifice, so to say, the 100% correctness, and we may gain a dramatic speed up.
Yeah. But it's not just speed up. There are also examples already here that we tested where the Risch algorithm does not work. Actually,
Yeah.
get those,
Yes.
and where we can solve them. So
Yes.
there's
Yes.
Yes, for non-elementary cases, this is true. Thank you, Ito, for adding that in.
Okay.
Anyway, this is really nice.
Thank you so much for the great questions. Are there any other questions?
So you mentioned that the system should be well, modular, right? So you can expand it with more tools and other LLMs, right? Do you imagine a future where you would get some guidance, maybe directly from the LLM or from, I don't know, some statistics, like what tools are missing, right? Like right now we have a box that translates, right, an integral to a series, or using the built-in SymPy implementation or whatever, right? But there might be like what other tool sets are missing. Do you understand my question?
I think so. You're asking if we can use the system to identify rigorous, like symbolic tool gaps in our.
Exactly. Yeah.
Okay, that's that's an interesting question. I've not thought about that. But once we have more data, once we continue to benchmark the system, we might be able to classify different integrals and identify patterns, like patterns of calling one tool and then another tool with a bit of help from the LLM in between, which bridges gaps. And if we identify such patterns of like sequences of calling tools, we could implement a new tool that does this automatically for us. This will require, of course, identifying these patterns. So hopefully, I'm sure we'll be able to do this in the near future when we begin to benchmark the system more fully. Thanks for asking the question.
Yeah, I see Wolfgang has a question as well.
Yes, I also have a question. You can add now a lot of tools behind the LLMs, computer algebra systems, etc. But you showed us already an example where the system hallucinated an explanation by saying, I ran some Python code and it confirmed the validity. So what does the LLM now prevent to hallucinate that it has called a computer algebra system and says, I verified the answer? So I think this is quite some fundamental problem, which somehow indicates there must be always an independent path towards verification for the user of an LLM that does not go through the LLM itself, which is always prone to hallucinations. Or do I overlook here something?
So this is a very good point. If we indeed give the LLM all of the power and allow it to say, I ran this, I ran that, then we could end up with a whole fabricated solution, which does not mean much. And really, this is one of the great, one of the goals in creating a three-part system is having this isolation between the parts. the validator's stamp will not be able to be fabricated by the LLM. And the tool systems are run on a CPU independently of the LLM. And this means that the whole thing is, the three parts are isolated. So we know exactly what is being called and whether things pass validation.
Yeah.
This is a great point.
Specifically for integrals, you can always either calculate a derivative and then check symbolically a match, if it's or you can actually numerically evaluate the integral, right? And then actually check numerically. So you get additional methods to check to validate whether the LLM actually did a good job. So, and this has to be done in an independent system that does not rely on LLMs at all, right? Only on symbolic algebra tools or numerical tools that are computing the integral independently. And that's something this is the way for us to independently verify.
Okay, thank you.
This is also for our previous project, Asimov, that Tomer mentioned, is something that where many today of the benchmarks for the quality of performance of LLMs in mathematics, even more broadly than integrals, are not validated in an independent manner. And that's something we developed over there so we can do an independent check for the performance of the LLM and not, for example, rely on other LLMs like some people do. Yes, there has to be an independent LLM-free validator.
Thank you so much for the question.
Okay, nice. Are there any final questions? If not, then
maybe a question concerning where you showed the pi formulas, where you managed to reduce 40% of the formulas and could connect it by one of your matrix representations for going through the two-dimensional grid of the matrices, right?
Yes.
Did you also, if you use this, did you find a heuristic or an explanation? What is maybe the best acceleration formula going diagonal? Or so if you know that, if you look at the best formula, how do you achieve it? Or maybe you find even a better formula from that you could connect. Have you looked at that?
That is one of the goals. We are trying to find good formulas for additional constants. For pi, and specifically the CMF, so far we've not been able to identify an irrationality proving formula, a good convergence formula.
But the best formula that you can get from this grid, maybe, I don't know.
Okay, for the best one, I think the exponential convergence rate, I can find this if this interests you. Just 1 second, please.
Could you go back to the corresponding slide as well?
Yes, I'm on my way there. Good idea. Okay, so this is the unification slide where we see all these formulas that originate from the CMF. Can you see this?
Yeah.
Okay, perfect. So in terms of convergence rates, just 1 second, please. It's a good question, and I came unprepared for this. I did not have a list with me, so I'm going to go to the appendix of the paper to find this for you.
But you see inside the circles the convergence rates and not the irrationality measures.
Yes, these are the irrationality
parameters. So actually, we are seeing that certain formulas converge more quickly than others. I think the best one that we see over here is this the one along the trajectory 112. I think that's the best one we marked in this figure.
That's
so
true.
Which is not sufficient for proving irrationality, but is closer than others. Generally, you can search.
But you have this class of formulas that you can get, and now the question is, what is of all the equivalence things that you get there, what is the best one?
In terms of irrationality measure.
Yeah. So, or what has the best to compute fastest the pi digits, let's say, something like that. Also.
So this is good, a good point. We have two different questions, the best irrationality measure and the best convergence. The best convergence we get in the 2, 1, 1 direction, which is labeled here in the minus 0.48 delta irrationality measure. So those are the fastest computing formulas, the most fastest converging formulas. And the best irrationality measure, as mentioned previously, is the 1, 1, 2 direction, which gives us Gauss's formula.
Okay.
We do have a few directions that I believe even improve this. I don't have them here with me, but I think we got down to minus 0.15 in terms of irrationality measure, or maybe minus 0.19. I can check this later if this interests you.
Yeah, generally
can
we
say
expect there to be a bigger CMF that will be more complex and will capture the formulas that are currently not unified by this one. And then we also expect that CMF to contain better formulas, both in convergence and in the rationality measure.
Interesting, thanks.
Can I a small question on a similar topic, and I hope my understanding is correct, but these you're talking about what a single direction along the CMF, which means that asymptotically you'll continue to advance along the same steps. But if I take a combination of directions and sort of define like multiple, like a multiple attractor system, like I go, you know what I mean? I iterate between different directions, then the average will not necessarily be integers in the average direction. So I might get all sorts of in between, and I'm staying on the CMF. So does that yield anything interesting? Am I understanding correctly? And is that even possible?
If I understand correctly, are you raising the possibility of perhaps going in nonlinear directions, like traveling in interesting, I don't know, spirals, or creating subsequences that like combine different directions?
I mean sequences of directions. So like I will go one step on 1, 1, 2, 2 steps on 2, 1, 1, another step on 1, like.
You could imagine, since each direction here is in the end a sequence of rational numbers, you could, for example, take pairs of numbers from two trajectories, each time two rational numbers, and average them or something, right? That's which does not mean necessarily that you're going that this is equivalent to the average, to the intermediate direction. And actually, I'm not sure what to expect. This will again be a rational sequence if you do that, right? And what will be the properties of that sequence? It's,
something that
that's
we
what I
haven't
meant.
explored.
Yeah, actually, I'm not sure. I don't know. This is an interesting question for us to. There are multiple ways to combine sequences of rational numbers. We can. It's not that clear whether that will always, for example, give you another sequence that lives inside the same CMF. Do we have this closure?
But generally, it's valid. I mean, you still expect to converge to the same. I mean, as long as it's periodic, then you are going in a certain sort of steady direction. So I don't know. My intuition, this is not strong, but you would intuitively assume that it will converge.
If it's
I will mention something, because this is a very good question, which also other members of our group are dealing with, both for the PyCMFs and other CMFs. So an interesting observation, which is not immediately clear from this image, but is true, it seems to be true in general, is that those measurements of convergence, either the convergence rate or the irrationality measure, are continuous in angle. Meaning, if you, for example, walk in some direction which is not a rational, steady direction, meaning taking, for example, instead of walking just one step to the right, then one step up, you walk Fibonacci numbers to the right and then the next Fibonacci number up, or something like that. That will mean you walk in some irrational direction. And so it's not immediately, it can't be codified as some simple continued fraction or something like that. It's more complicated. However, the behavior when it comes to convergence and the rationality measure is actually pretty well understood because of the fact that as you go in some direction in this lattice, your behavior when it comes to convergence and irrationality measure is continuous. So you can look at a rational direction which is very close to that weird direction, and that similar rational direction will have very similar properties. And so you can actually as long as you are going away from the 0, 0, 0 point, your behavior is actually pretty well understood because of this continuity, which is non-trivial and pretty difficult to justify in general, but seems to be the case.
You're continuous in angle with the angle. Oh, in order to, okay, if you go far enough, okay, yeah, sorry.
Yeah, that is also opens up the properties for optimization, which is something we have explored. So you can sort of look to some gradient descent algorithm or something like that to improve your rationality measure. It's an interesting idea which we are actively working on.
Thank you.
Thanks, Shachar. That was both a fascinating question and a fascinating answer. Thank you for adding that information.
Wonderful. Do we have any final question or remark? If not, then we close the session. Thank you very much, everyone, for joining in. Well done, Tomer. This was very well done. Really happy that we had it. Great job. Good luck. Good luck with finishing the thesis. So,
Thank you so much. Thanks, everyone, for joining. It really is an honor to have everyone.
I think we should give some applause to the speaker and congratulations to his
Super.
achievements.
Thank
Well
you so
done.
much.
Yeah,
Okay.
Thank you,
impressive.
guys.
excellent. Thanks, everyone. You can also stop the recording, and we'll definitely keep the file for